So when we convert from ratio to angle, we usually use our calculator to do that, to be able to go from an angle description of that position to a ratio description of that position. We need to usually use our calculator. However, we want to avoid doing that when we don't have to. And there's two situations where we don't have to. In fact, you'll be required to do this without a calculator, is when we have a 30-60 triangle or 45-45 triangle. And because of the symmetry that the 30-60 triangle comes from, is basically half of an equilateral triangle. We know that these three triangle sides are the same, so that means the base is going to be exactly half of this length. And we can also calculate the exact value of the vertical component here using Pythagoras. With the 45-degree angle, we know that the symmetry is exactly half a square. Okay, well, we know that if we split a square in half there, those angles are going to be 45 degrees. And we know that all four sides of that square are going to have equal length. And knowing two lengths of that square side, we can calculate the diagonal length, which is square root 2 using Pythagoras. Now these, if you remember where the shapes that they come from, it is easier to memorize these ratios. But you do need to memorize these ratios. And not only that, we're going to have to find all these special angles in the circle now, since we're doing circle trig. So when we talk about these special ratios and special angles, we need to use exact values, not just for the side lengths, but for everything, from going from angle to side length as well. So for example, here's 210. If I draw 210, 210 is in this position right here. Okay, there's 210 degrees in standard position. Now the triangle that's associated with this happens to be a special angle. Okay, because the reference angle here is 30 degrees. That's 90 degrees, so this makes it a 30, 60, 90 triangle. And to be able to find the trig values for this, we don't use our calculator. Although a calculator gives us the same decimal values, we're going to keep it in exact values. So for example, cosine of theta then works out to be, well, cosine, this triangle is going to have -1 to -√3. Okay, when I relate it to this triangle here. And again, make sure that, I'm just going to highlight this, we are dealing with positioning. So to the left √3 and down 1 is different than up 1 or right √3. So that's really important when we talk about the ratios. So the cosine ratio becomes -√3 over 2. The sine ratio then becomes -1 over 2. Okay, so it's no longer just a triangle, because if we're talking about the positive values, we're talking about just in quadrant 1. We are not in quadrant 1 anymore, and we need to distinguish this position from the quadrant 1 triangle. The tan ratio is going to be the slope. The slope is positive because it's going up like that. Okay, it's going to be -√3 over -1, which simplifies to +√3. And the reference angle that refers the shape of the triangle is going to be our 30-degree angle. And the reference triangle is always made with the x-axis. Okay, although there's a similar triangle that we can make here along the y-axis, we don't ever use that one. We always make our reference triangles with the y-axis, sorry, the x-axis. We always draw it from the point vertical line either down or up to the x-axis.